Hey guys, today I want to present a solution to IMO 2019 problem 1. Firstly, let's take a look at the problem statement. We are asked to determine all functions f from integers to integers such that for all a and b the following equation 1 holds. F of 2a plus 2f of b must be equal to f of a plus b. We see on the right hand side an expression of the form of f of something. These are always not that easy to work with. Therefore, we want to eliminate it somehow. Furthermore, it is always a good idea to substitute 0 for some variable in such a functional equation. We combine these two to make the following substitution for a and b into equation 1. We substitute 0 and a plus b in 1, which gives us f of 0 plus 2f of a plus b equals f of a plus b. We can substitute this equation number 2 in 1, which gives us f of 2a plus 2f of b, which is equal to f of a plus b, and therefore also equal to f of 0 plus 2f of a plus b. Now we see that we have an equation, a functional equation over the integers, and an expression of this form. This motivates us to use induction. Here we have a term with the form f of b, and here we have f of a plus b. If a were some constant integer, then we could relate f of b and f of a plus b via some other constant, namely f of 2a minus f of 0 divided by 2. Therefore, we're going to plug in the smallest positive integer, which is 1, into a. So we let a equal to 1, which gives us f of 2 plus 2f of b equals f of 0 plus 2f of b plus 1. Rearranging this equation gives f of b plus 1 minus f of b is equal to f of 2 minus f of 0 divided by 2. We will call this constant m. Now we can see immediately that it follows that f must be a linear function, because the difference between two consecutive values of f is a constant, namely m. We can easily prove this via induction to the left from f of 0 and another induction to the right from f of 0. But we will not do that in so much detail right here. So we obtain that f of b is equal to f of n times b plus some other constant n. Plugging all of this back into our equation 1 gives us m times 2a plus n plus 2 times mb plus n is equal to n times ma plus b plus n plus n. Now we want to make some simplifications. So we have 2m times a plus b plus 3n is equal to m squared a plus b plus m plus 1 times n. So because we can choose a plus b freely, we have 2m equals m squared, as well as 3n equals m plus 1 times n. Therefore, 2m equals m squared, and 3n equals m plus 1 multiplied with n. So we know that every function f that satisfies the given conditions is of the form mb plus n, where 2m equals m squared and 3n equals m plus 1 times n. Therefore, we have two cases. First, case being m equals 0, and the second case is m equals to 2, which follows from this equation. N equals to 0 yields 3n equals n, which implies also n equals to 0. Therefore, f of b equals 0 for all b and z. And by plugging this into our equation 1, we see that we have 0 plus 2, 0 equals 0, which is true for all b, and therefore this is in fact our first solution. And in the second case, we obtain 3n equals 2 plus 1 times n, which is also 3n. Therefore, n is just some integer. And if we plug these numbers in, then we get that 4a plus n plus 4b plus 2n equals 2 times 2a plus b plus n plus n, and this is equivalent to 4a plus b plus 3n equals 4a plus b plus 3n, which is in fact true for all integers a and b. Therefore, f of b equals 2b plus n for n in z is a solution for all b and z. This is our second type of solution, and since we've finished all of the cases and checked both the solutions, we know that these are the only two types of solutions, and we are done.